got a question here about half-life, and they're using dice to sort of model the decay of radioactive atoms. So they're rolling dice. You don't know if you may have done this in the classroom where you model it and then you take away the dice that come up on a particular side, and then you're rolling the remaining dice. And this kind of models the atoms decaying and changing, and therefore you have less and less of the original atoms as time goes by. And so we've got a set of results here, and it asks for 2 reasons why it's a good model for the random nature of radioactive decay. So you couldn't just say because it's random, because it kind of gives you that in the question. So you'd have to talk about how this is similar to the atoms decaying. And really the 2 kind of key similarities here are that you can't tell when a particular dice is going to change, and you can't tell in a similar way when a particular atom is going to change, and you can't tell which dice is going to change, and likewise you can't tell on this model which dice is going to come up in 6. So the 2 answers they're looking for here is that you can't tell which one, and you can't tell when. Okay, so you're not sure which ones are going to change, and you're not sure when a particular one's going to change, and in that way it's similar to radioactive decay. Okay, so they plotted the graph for us. That was nice of them, and it asks us to use this to work out the half-life. So whenever you're looking at a half-life curve, and if we look at this curve, we can see that it's an absolutely classic half-life curve. But whenever we look at that, what you really want to do is, if you can, look at the first number, the starting activity, or the starting number of dice, or the starting number of atoms, and then you just take that and you just half it. And that gives you half the activity, or half the number of dice. So the question is, how long has it taken to get to there? Well, half 100 is 50, so how long has it taken us to get to 50? And we go way down there. And that looks to me to be around about 3.7, 3.8. Let's call it 3.7 rolls. And you can say, well, hang on a minute, you can't have 0.7 of a roll. No, you can't. But you're rolling so many dice, you're allowed to say, on average, 3.7 rolls will get you to halfway. So even though you're not allowed to have 0.7 of dice roll, you are still allowed to describe this as 3.7 rolls. Okay, they've got this fancy chemical called proactinium. Okay, it's dark. Our little generator is producing some of it, and it's got a half-life of 70 seconds. Okay, it starts with some uranium that decays into thorium, and that alpha radiation is emitted. Okay, so it's asking us to complete our little decay equation here, and to do that, really, you've got to know what's going on with alpha. So our alpha is 2 protons and 2 neutrons. That's an alpha particle, and that means it's got a mass of 4 and an atomic number of 2. Okay, and look at our uranium. Our uranium has started with a mass of 283, and it's turned into thorium, which has got 234. So it's lost 4 mass. There's the 4 mass. And it's also going to lose, it's also going to lose 2 protons. There's our atomic number. So the atomic number of thorium, my mistake, draw on the fact that it's, yeah, that's right, I haven't made a mistake. Yeah, so that is 90. It's changed to 90, so our atomic number of thorium will be 90. Is 90 a reasonable thing for an atomic number to be? Yes, your radioactive materials are going to be sort of 80s, 90s. You can even just about go into the hundreds for the really unstable ones. Okay, so our proactinium decays, forms a new element, radiation is emitted. So it's given us some more information. Okay, so here's our proactinium, and it's turned into a new substance plus some radiation. So first thing, use the information from figure 2 and figure 3 to determine the name of element X. Well, element X has got 92 protons. So whatever element X must be, it must have 92 protons. Well, here we have something with 92 protons already. It's uranium. Okay, the fact that it's got a different atomic mass doesn't make any difference to the element. It just means it's an isotope of uranium, but it is still uranium. So we are looking at the name is uranium. Okay, and then final part of the question, type of radiation emitted. Okay, so now what's going on here? We've got 91 protons over here. We've got 92 protons over here. So what's gone on is one of our neutrons has turned into a proton. We've gained an extra proton. And the only time you get in radiation when that happens is if you get an electron given off, bits, which is beta radiation. Okay, so our answer is it's beta radiation. And why is that? It's because we've gained a proton, and that and when that happens, we also get an electron released when that's beta radiation. So two parts of the question, one on half-life and one on those decay equations.